Hey guys, this video is solely devoted to analyzing a pendulum using conservation of energy. So the first thing I want you to do is just copy this down, and I'll pause real quick while you do that. But first I want to just point out title, fill in the blanks, a little hook with the ceiling there, and 5 positions, A, B, C, D, and E, with the same chart you've been seeing for GPE, KE, and total energy next to it. I did label the ground down there. C, we're going to say, is at ground level. There's no height. You could write that down as well for letter C. And D and B, I drew a little dotted line just to say D and B are at the same height. Okay, the same height. And letter A here, we're going to say that's where the pendulum is released. Somebody's hand is holding it there, basically, and it starts at rest at that location, all right? And I'll pause real quick, and you could copy that down, and then we'll analyze it and fill in the blanks. Alright, so we're back. Let's write some numbers down here. We could say maybe a 10 for GPE there to start. And because it starts at rest, we could also say that the kinetic energy is 0. Alright. And then it swings down. Maybe we can say here that the GPE is 4 at letter B. Give that as a given piece of information. And at letter D, it's at the same height, so it must have the same GPE. It's the same object at the same height. So that's going to be a GPE of 4 as well. Well, that same thing applies for A and E. We're going to say E is at the same height. So E is going to have a GPE of 10 as well, all right? So how could we fill in the rest of the blanks? Well, let's look at letter A to start. We have the GPE and the KE at that location. We could add those two together and get the total. So the total's 10. And what do we know about the total? It stays, that's right, I'm glad you said it, stays constant. The total stays 10. So once you know the total at one place, you know the total everywhere else. Okay. So it looks like at most spots what we're missing is just the KE. Here, here, and here, missing the KE. But at letter C, let's get the GPE there first before we finish up with the kinetic energy. Letter C, the height is 0 because it's at ground level. So if you plug 0 into the GPE formula for height, you would get a GPE of 0. When you're at ground level, your GPE is 0. All right, so that means that all we have to do is some subtraction to get all the kinetic energies. We could do the total minus the GPE at every spot. 10 minus 4 is 6. 10 minus 0 is 10. 10 minus 4 is 6. And 10 minus 10 is 0. So we filled in all the blanks. Now, using this diagram, I want to answer several questions about a pendulum. And you're going to need to copy them down one at a time as we go through them, okay? So here we're going to start with question 1. Right here, copy it down. It says, where does the pendulum move the blank? Oh, well, we're going to start with asking, where does the pendulum move the fastest? And the fastest spot for the pendulum will be wherever it has the most KE. So, and the spot where it has the most KE is where it has the least GPE, because it lost all the GPE and gave it to KE instead, okay? So wherever it has the most KE, it's going to have the least amount of GPE, and it'll be moving the fastest. Where what spot has the most KE and also the least GPE? Well, it's the lowest spot. The lowest spot, letter C, has 0 GPE because it has no height, and that's why it has a lot of kinetic energy. So it would be letter C. So vice versa, wherever it's moving the slowest is where it has the least kinetic energy. Wherever it has the least kinetic energy and the most height or most GPE. So for the slowest, we could look at the tallest positions because they both have 0 kinetic energy. So we could say A or E is where the pendulum is moving the slowest because they both have 0 speed. You have to say both of them. All right, question 2. At which point does the pendulum have the same speed as position B? Where is the velocity the same as B? Is there another letter that has the same velocity as B? Well, I don't see velocity anywhere on that diagram. That's confusing. How can I figure out which one has the same velocity as letter B? The box doesn't have anything for velocity in it. Well, we still could figure that out because velocity comes from kinetic energy, all right? So if we look at position B, because it has 6 joules of kinetic energy, we know it has a moderate speed, but wherever the kinetic energy is the same, that's where it will have the same velocity. So actually, at equal heights, the pendulum has equal velocities. So D has equal velocity, write this down, to B because they have equal heights and therefore the same kinetic energy. So because they have the same height, they get the same kinetic energy, and if you use the formulas, you would end up with the same velocity. Number 3 and 4 will be our last ones for this video, all right? So if you hold this pendulum to your nose when released at letter A, why does it not smack you in the nose on the way back? You saw that in a previous video. It's pretty cool. You could hold your nose up to the pendulum, let it go. Don't push it, let it go only. If you push it, you give it kinetic energy. We just want to let it go, give it 0 kinetic energy. And it comes back right up to your nose, but doesn't smack you in the nose, all right? And it has to do with the fact that the total stays the same. In this example, because the total is always 10 joules, it cannot go higher than the GPE it started with. So if you release it from here, it can't swing back up higher, because that would mean it had 11 joules. Had more energy, and where did it get that from? Nobody was pushing it, all right? It can only, if you let it go, the total's always going to say 10 joules in this example. It's never going to get energy from nowhere. So it climbs back up, and the GPE goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 joules of GPE, but can't get 11, so it doesn't smack you in the nose, all right? It cannot go higher than the GPE it started with. Okay. Number 4, last one. Why is the energy of every swing of the pendulum slightly shorter than the first swing? You might notice with a swing at the park, if somebody sits on a swing, or if you do, you slowly go lower and lower and lower with every swing. You don't swing as high as the first swing. Each successive swing is slightly lower, and it really has to do with the fact that you're not losing energy it's not like you're not conserving energy. it's that I kind of lied to you on the first video, is that this formula, when we use it, GP and KE, there's always like a third term on, which is thermal energy. So in the hook of the swing, if you hear creak, 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 really what's happening is some of that energy is changing from GPE and KE into sound and heat energy. Kind of like if you rub your hands together, do this right now, what you're going to see is that the kinetic energy of your hands is turning into thermal energy. So thermal energy is produced through friction, and that happens in the pendulum, and you might seem like it's losing energy overall, but it's not. It's just changing some of its energy into heat. So so we are finally write down some energy changes into heat, and you cannot really recover it. Cannot recover it. All right, guys.